Welcome to the deep dive. Okay, let's jump right in with a question for you listening right now. Think about your phone, your computer, maybe even those huge AI servers churning out amazing stuff. What's the single most vital piece of hardware inside that's almost invisible but makes it all think?
Yeah, it's funny. Everyone always thinks CPU, right? The processor. Iron Man in the Marvel movies, the super smart,
Yeah,
obvious hero.
it's the star of the show.
Yep.
But even Iron Man needs his power source, doesn't it?
Exactly. Without that core power, the hero can't do much. And in the digital world, that power source, that arc reactor, is dynamic random access memory, DRAM. That's the main memory dictating how fast everything really runs.
So today we're diving deep into DRAM's story. We're using a great source, the Literature Survey on DRAM, history, usage, and device-level structure as our guide.
Our mission really is to track how this tech evolved from, its surprisingly simple start back in the 60s all the way through the speed bumps like DDR5 and now, well, how AI is pushing it into totally new shapes.
And by the end, you'll have a much better feel for this invisible engine that honestly limits or enables pretty much every device you own.
Okay, so where do we start? The history. To really get why DRAM was such a big deal, you have to look at what came before.
Right, the before times. That was static RAM, SRAM. And the survey points out it had a major drawback, didn't it?
Oh, absolutely. SRAM worked, it held data reliably, but wow, was it inefficient for main memory. Think about this. Storing just one bit, a single 1 or 0, took 6 transistors.
6. Just to hold one bit.
6 separate transistors. Now try building, say, your laptop's memory, billions of bits with 6 components per bit. It just wasn't scalable, way too complex, way too expensive.
That does sound like a dead end for building powerful computers. So who broke that logjam? Where did the breakthrough come from?
That was Dr. Robert Dennard over at IBM's Thomas J. Watson Research Center. Back in 1966, he was looking at MOS technology metal oxide semiconductor and had this really elegant idea.
What was the core insight? What did he see differently?
He basically realized you don't need all that complex circuitry just to hold the data state. You just need something that can hold an electrical charge. So he used a capacitor for that. Charge it up, it's a 1 quart. Let it discharge, it's a 0.
Okay, so the capacitor holds the state.
Right. And then you only need one single MOS transistor to act as a switch or a gate to control access, letting the system read or write that charge.
Wow. From 6 components down to just 2. 1 transistor, 1 capacitor, the 1T1C cell. That's incredibly simple. He patented that in 67, right?
Yep, got the patent in 68. And while the very first commercial chip came out shortly after, the real turning point, the one that changed the industry, was Intel's 1103 chip. That landed in October 1970.
Ah, the 1103. I've read about that one.
Designed by Joel Karp, laid out by Pat Earhart, the survey highlights it became the first commercially successful DRAM, and it took off fast. By the mid-70s, it had pretty much replaced the old magnetic core memory. That 1T1C design became the standard.
It's kind of amazing that this basic design from, over 50 years ago is still fundamentally what's in our devices today.
Okay.
But if it's that simple, just a transistor and a capacitor, there must be a catch. Why the D in DRAM, the dynamic part?
Ah, yes, the catch. That simple capacitor, while cheap and small, isn't perfect. It leaks. Think of it like a tiny bucket with a slow, microscopic leak.
So the charge, the data, just drains away over time.
Exactly. If you just store a 1, a charged capacitor, and leave it, eventually that charge leaks out and poof, it becomes a 0. Your data disappears. It's dynamic because the state isn't permanent.
Okay, that sounds problematic. If the memory is constantly forgetting itself, how does anything actually work? How do we keep the data alive?
Constant vigilance. You need a refresh function. The system can't just write the data and walk away. It has to periodically go back and read the data, then immediately write it back fully charged, essentially topping off all those tiny leaky buckets.
And this has to happen really fast, right? The survey mentioned a time frame.
Incredibly fast. The standard requires every single memory cell to be refreshed within 64 milliseconds.
64 milliseconds. That's less than the blink of an eye. And it gets worse if the chip heats up.
It does. Above 85 degrees Celsius, that window shrinks to just 32 milliseconds. So the memory controller, the chip managing the DRAM, is constantly working in the background.
How does it manage that across potentially billions of cells?
It sends out thousands of commands. Typically, it issues 8,192 auto-refresh commands within that 64 millisecond window. Each command tells a whole row of memory cells across different banks to refresh themselves. It works out to a refresh command roughly every 7.8 microseconds.
Wow. Non-stop micromanagement just to maintain the status quo. Okay, wait, there's another weird thing in the survey. Something about reading the data. Does simply reading a bit in DRAM actually Erase it. That sounds backwards.
It does sound backwards, but yes, that's one of the quirks of DRAM. When the transistor opens the gate to let the sense amplifier read the charge in the capacitor, that tiny charge gets shared onto the bit line. The act of reading itself disturbs the charge, potentially draining the capacitor just enough to lose the state.
So every time you access data, you risk destroying it. How did they solve that? That seems like a fundamental flaw.
More clever engineering. They built in sense amplifiers. These circuits are crucial. When a cell is read, the sense amp does two things almost simultaneously. It detects that very small voltage change on the bit line to figure out if it was a 1 or 0, and it immediately amplifies that signal and writes the full charge back into the capacitor it just read from.
So the read operation itself forces an immediate refresh of that specific cell.
Exactly. It's a built-in fix. Reading inherently includes restoring. Pretty smart, right? It solves the destructive read problem and ensures the data stays intact even during access.
Okay, that makes sense. Elegant solutions to tricky problems. So once they had the basic structure and the refresh mechanism sorted, the next big push was just speed.
Speed, speed, speed. And efficiency too, but mostly speed. The first big step was synchronizing the memory with the processor. Before about 1997, memory was often asynchronous, meaning it wasn't perfectly timed with the CPU's clock. This led to delays, waiting states.
Then came synchronous DRAM, SDRAM, aligning memory to the CPU clock.
Right, that was a big improvement. But the real revolution for performance was double data rate, DDR, which started appearing around the year 2000.
DDR. We still use that naming convention today. How did they double the speed without just cranking up the clock frequency, which causes other problems?
They got clever about how they used the clock signal. Think of the clock signal like an oscillating wave. Older memory systems only transfer data on the rising edge of that wave.
Okay, like only using the upswing.
Exactly. DDR technology figured out how to transfer data on both the rising edge and the falling edge of the clock cycle. 2 transfers per cycle instead of 1. Double the data rate.
Double the throughput without doubling the clock speed. Make sense? And we've just been refining that approach ever since.
Pretty much. Each generation got faster and usually more power efficient. The survey mentions key steps. DDR3, around 2007, was a big deal for laptops because it dropped the operating voltage to 1.5V, saving significant power.
Then DDR4 came along in 2014. That introduced bank grouping, right? A way to access different parts of the memory more efficiently to hit higher speeds.
Yep. And now we're well into the DDR5 era, which started rolling out around 2020. DDR5 is another significant jump. It has a wider prefetch, grabbing 16 bits of data ahead of time instead of 8. Plus, it has things like on-die error correction and even power management integrated right onto the memory module itself, all adding up to way more bandwidth and better reliability.
That focus on bandwidth seems crucial, especially now. It feels like the single DRAM standard is fracturing, specializing for different needs, like mobile versus, say, AI servers.
That's exactly what's happening. One size doesn't fit all anymore. For anything mobile phones, tablets, even increasingly complex systems in cars, the absolute killer constraint is power consumption and heat.
You can't have your phone burning a hole in your pocket.
Right, so that drove the development of low-power DDR, or LPDDR. It's DRAM optimized purely for efficiency. It might sacrifice some raw peak speed compared to desktop memory, but it sips power.
The latest is LPDDR5X.
Yeah, LPDDR5X is pretty amazing. It hits speeds up to 9,600 megabits per second, which is faster than older desktop memory, but does it with about 25% better power efficiency than the previous LPDDR generation. That's how you run complex stuff on a phone battery.
So LPDDR is the efficiency king, but then you have the other extreme, artificial intelligence, high-performance computing.
Yeah.
They need bandwidth above all else. Forget sipping power. They need a fire hose of data.
And that's where high bandwidth memory, HBM, comes in. This is maybe the biggest architectural shift since Dennard's 1T1C cell. It tackles the problem of data movement fundamentally differently.
Instead of chips spread out on a board, HBM goes vertical.
Exactly. Instead of long wires on a circuit board connecting the processor to rows of DRAM chips, which limit speed and burns power, HBM stacks multiple DRAM dies directly on top of each other.
Like building a memory skyscraper instead of a sprawling suburb.
Perfect analogy. And they connect these stacked dies using tiny vertical wires called through-silicon vias, or TSVs, that go straight through the silicon layers.
Super short, direct connections.
Ultra short. This dramatically cuts the distance data travels, allowing for massively wider interfaces, think thousands of lanes instead of just 64, and delivering enormous bandwidth with surprisingly good energy efficiency per bit transferred. HBM is basically non-negotiable now for training large AI models.
And this intense demand for HBM, especially for AI, is actually shaking up the whole DRAM market structure, isn't it? The survey had some interesting figures.
Yeah, it's a huge deal. The market's long been an oligopoly dominated by Samsung, SK Hynix, and Micron. Samsung's been the leader for years, but
But SK Hynix made a big bet on HBM early on.
they did, and it's paying off spectacularly. The survey highlights projections that SK Hynix could actually overtake Samsung in DRAM revenue by 2025, largely because of their strength in HBM. They estimate HBM could be 42% of SK Hynix's DRAM revenue next year. Back in 2019, it was just 3%.
Wow, 3% to potentially 42% in about 6 years. That shows you where the market heat is. It's the AI effect rippling right down to the silicon manufacturers.
Absolutely. The AI gold rush is reshaping the fundamental component supply chain.
But even with clever stacking like HBM, the underlying 1T1C cell itself is hitting physical walls, right?
Yeah.
We can only shrink things so much.
We are definitely pushing the limits of physics. The leading edge is down to what they call 1-alpha nodes. We're talking features just a handful of nanometers wide. Making these requires extreme ultraviolet, EUV, lithography. The manufacturing process involves over 1,000 steps. It's incredibly complex.
And the survey mentioned these crazy structures they have to build now, like trench capacitors.
Yeah, to get enough capacitance, enough charge storage in such a tiny area, they have to etch these incredibly deep, narrow trenches into the silicon. The depth to width ratio can be over 50 to 1.
Like digging tiny microscopic wells just to hold a single bit's worth of charge.
It really illustrates how hard scaling has become. You can't just shrink things proportionally anymore. You need these heroic engineering feats.
So if shrinking in 2D planar scaling is running out of steam, where does the industry go? We saw stacking chips with HBM. What's next?
We go 3D again, but in a different way. The next big frontier is likely monolithic 3D architecture. This isn't just stacking finished chips, it's about building the memory cells themselves vertically, layer by layer.
So truly three-dimensional memory arrays.
That's the vision, stacking the actual transistors or capacitors on top of each other. Samsung is already talking about early versions using vertical channel transistors, possibly by 2025, aiming for more complete 3D stacking structures by 2030. The potential density gains are huge.
This all seems aimed squarely at tackling the infamous memory wall, right? The problem where the super-fast processor spends most of its time just waiting for data to arrive from the slower memory.
Precisely. For decades, processor speeds increased much faster than memory speeds. That gap, the memory wall, is the key bottleneck in many systems today. HBM helps, 3D DRAM will help more.
But the ultimate solution might be even more radical.
The really futuristic idea, though it's becoming less future and more now, is compute and memory, or CIM.
Processing inside the memory.
Exactly. Instead of constantly shuffling data back and forth between the memory chips and the processor chip, which costs time and energy, why not perform some computations directly within the memory array itself?
To bring the computing to where the data already lives.
You got it. Companies like D-Matrix are pushing this hard, developing what they call 3D digital in-memory compute, 3D IMC. They integrate logic right into the memory stack. The claim is potentially 10x performance gains over systems using separate HBM and processors because you eliminate so much data movement. It changes memory from passive storage to an active computational unit.
That feels like a truly fundamental shift. From Dennard's simple 1T1C cell just holding charge to memory that actively thinks.
It's been an incredible arc of innovation, driven by constant need and brilliant engineering.
Okay, let's try to boil this down. If you remember just a few things from our deep dive today based on that literature survey.
First, never forget the foundation. That incredibly elegant, simple 1T1C cell from Robert Dennard. It's been tweaked and shrunk for 50 years, but it's still the heart of it all, the atom of digital memory.
Second, one size no longer fits all. The market has split. You've got LPDDR pushing the boundaries of power efficiency for everything mobile, and then you have HBM delivering the massive bandwidth needed to feed the AI beast. Specialization is key.
And third, the future is vertical. When shrinking hit the wall, innovation went upwards. First stacking chips with HBM, and soon stacking the memory cells themselves in 3D architectures. And beyond that, integrating computation right into the memory fabric.
So here's something to chew on. DRAM, by its very definition, has always been temporary storage, this leaky bucket we have to keep refilling. But if we're now physically merging this temporary storage with permanent processing logic, are we fundamentally changing what memory even means? And, how close we're really getting to the absolute limits of what we can compute with silicon?